Finding the coefficients and free terms of canonical equations of the displacements method. This is the presentation of the articles 3.16 and 3.17 from the book Mechanical Systems Calculations of the Marine Facilities. Let's consider the frame, 4 times statically indefinable frame, shown on the figure 3.16.1 on the left A, the assigned system, and it is assigned to decide the frame by the method of the displacement, the method of this assignment, and the decision is finding of the displacement, because if we have the displacements of the mechanical system characteristic points, so we will have the required unknown variables due to the system statically indefinable. So we will have these variables, and after that we can decide all system by the we can find the appropriate forces or efforts, maybe moments, action, and the definite characteristic point of the mechanical system, and we will have the complete set of the equations together with the balance equations, and we can find the all support reactions and all efforts in the elements of the mechanical system. Sorry. So we have the mechanical system are shown on the figure 3.16.1a. This is 4 times statically indefinable system. So it's to use the displacement method. First, we have to do the main system of the displacement method. The main system is the assigned mechanical system, but in the definite places, we have to add the extra reactions, extra supports. Extra support could be the sliding embeddings, or it could be the extra rod connections to limit the displacement of the mechanical system. And that is those we will be able to find, to draw up the canonical equations of the displacement method and to find the displacement of these points. So the question arises, what is the degree of the kinematic indeterminants of the mechanical system? So statically, this is 4 times statically indefinable system, but yeah, I will not do in the deep in the subject how to determine the static indefinability. Everybody can find it, and we have to find the degree of the kinematic indefinability. Kinematic indefinability consists of the number of the possible number of the angular indefinability, number of the linear displacement indefinability. So this together two summands characterizes the kinematic indefinability. So the number of the angular indefinability for statically indefinable system, we have just counting the number of the nodes of the connection of the elements of mechanical system, or the rigid nodes. We have 2 here. So if we will look at the system attentively, we have the left one stand. Stand is 2L of the length. In the middle of the stand, the concentrated force is applied. Each L size is 2 meters assigned. And we have the rigidly connected to the stand the horizontal beam. The horizontal beam is the evenly distributed load Q. Low case is equal to 3 kilonewton per meter. The force is 5 kilonewton, and the span between the stands, 3 stands, all 3 embedded. For the rigid we see the rigid embeddings. The span between each 2 is 2 meter L equivalent. And how many rigid nodes we have? The first one, the connection of the vertical stand, the left one, and the horizontal beam. This connection is rigid. The second is the connection here. It looks like a hinge, but the hinge is the attachment of the second stand to the horizontal beam. So this is a hinge between the stand and the beam, but this beam is continuous, is continuous and is rigid. This connection of two parts of the beam in here rigidly connected. And the second one hinge. So we have one node and second one rigid node. So is the number of the angular mobility, immobility of the system is 2, and the number of the linear is to find the number of linear statical linear index of the linear kinematic indefinability. We have to consider the system as the hinged, as a hinged scheme, hinged mechanical scheme. So in each nodes we put, instead of the connection, just a hinge. Here we have a hinge. Here we can put the hinge between all three connected parts of the mechanical system, and here we will install the hinge, and all supports will be hinged in the hinged scheme. And we can define that only one motion is possible in the hinged scheme, is the transverse motion of this one beam, and accordingly the angular motion of the stands, if we have hinges here. So we have 1 degree of linear kinematic indefinability and 2 degrees of angular kinematic indefinability due to the number of the rigid nodes. And the total kinematic indefinability we can determine as 2 plus 1 equal to 3. So we have to have for the main system for this definite one assigned statically indefinable system, for the displacement method, we have to add 3 extra connections. 3 we can put here in the nodes, in the rigid nodes, in accordance with the determination of the angular immobility of the system. We put 2 sliding supports. This is sliding supports. This supports constraints, each one support constrains the angular displacement of the mechanical system in this support, but do not constrain the linear displacement. So this sliding support can move linearly to the components of the vertical motion, horizontal motion, the same as in supporting the second node. We indicate the second node, and third node we indicate this one. The third node is hinge in the assigned system. Second is a node, because we have continuous beam horizontal on the up part of the mechanical system. And this is the hinge. Here, because we have 1 degree of the linear kinematic indefinability of the mechanical system, considering the hinged system of the assigned system. So we will use the extra rod as extra support, which limits the horizontal motion of the system of this straight line of the nodes with the horizontal part of the system. This is the third number of the extra connections for displacement method. So we have the main system with these 3 displacement and constraint of displacement by 2 sliding embeddings and 1 hinged extra connection. After that, we have to find the diagram of the bending moments. Finally, we have to determine the factors in the summands of the canonical equations of the displacement method. We will obey the assumptions of the displacement method. The assumptions are that we consider the nodes, that the angle of the rotation of nodes of 2 connected elements mechanical system and the rigid nodes rotates for the same angle. We assume that do not consider the deformation of the system by the transverse forces, and the longitudinal forces do not impact the sizes of the system. We do not consider displacements of the system of the system and the influence of longitudinal and transverse forces, just only the bending moments. as the displacement of the bending moments by the magnitude are predominant deformations in the parts of the predominant deformations. And all other assumptions we adopt of the canonical equations of the displacement method and use the canonical equations, we have to find the factors of the canonical equations. Factors are the forces and the kinematic action of the unit displacement in the substitute in the added extra connections. We have 3 added extra connections. If we assume that these extra connections will move for in the direction of the constraint of the mechanical system, this is definite one connection. If we assume that perhaps if this connection will move for unit magnitude of the displacement, how much it impacts in the bending moment section and the elements of the mechanical system. And besides, we have to assume that by the introduce of the extra connections, we just divide the assigned mechanical system, making the main system of the displacement method. We just divide the assigned mechanical system into the statically indefinable 2 supports and 1 span beams of other kinds of the beams, like the element of the mechanical system, supported. It could be the embeddings of the ends of the beam and sliding embeddings. It could be the hinges at the ends of the beams. So to find the factors in the canonical equation of the balance of the displacement method, we consider 4 diagrams. We consider here 4 just because we have 3 time kinematically indefinable mechanical system, deciding with the use of the canonical equations of displacement method, and for each of the added support or sliding embedding or just extra supporting rod, we just have to develop the diagrams of the bending moment in the system elements for the assume that if this definite one extra support will move for the unit displacement, for the unit magnitude of the displacement. Yes, and for example, for the if we consider the support, extra support angular sliding embedding applied in the node of the mechanical system assigned or the connection of the left one vertical stand to the horizontal beam, if this support could rotate for the unit angle. And besides, within the assumptions of the displacement method, let me please remind, we adopted due to the smallness of the angles of rotation, the tangent of the angles, we assume equal to the angles, exactly determined in the dimension of radian. For each one single 2 supported statically indefinable beam within the mechanical system, which we consider separately, if we consider the main system with the displacement method with the addition of the extra supporting connections limiting the displacements. So we have previously taken decision usually. So in the textbooks of the structural mechanics, in the chapter of the displacement method of the decision of the mechanical system statically indefinable, or in the directories available online, we have a lot of the tables containing the previously got decisions of the single span 2 supported mechanical rods. So we can use these diagrams and these supporting reactions indicating the decisions of the 2 support, the 1 span, mechanical rods from directories and from the textbooks. This is one of the advantages of the use of displacement method, that this method allows us to use the previously got the decisions for the parts of the mechanical system, for the parts when we share, when we divide the mechanical system into the single span to support statically definable parts, statically definable beams. So we can use, if we assume that here we have the rotation moment of the left one, no other forces acting, because under the action of the transverse transverse force applied F, concentrated applied rightward on the stand, on the left one stand here. We don't consider, we just only consider the bending moments which arise due to the unit displacement, angular displacement in this definite one forced sliding support, as this is diagram under the action of kinematic action of the unit displacement in the force support, the direction of displacement angular. And that's why, because the assigned support, actually, we assume as the constraint of the angular displacement. That's why we consider what if this support rotates, definite one sample, clockwise for the one, for the one, any one unit. It's not so much important what 1 meter, 1 centimeter, it's not so much important, just we say unit displacement, unit one. And we first have this, to have this diagram. The bending moment in the horizontal hinge from this angular displacement is not distributed on the right part of the horizontal beam, due to the, here we have the sliding embedding, which constrains the next rotation. We consider this definite one bending moment diagram and the action, kinematic action of this unit displacement, only the adjacent parts of the mechanical system to this definite one node, assuming that other elements mechanical system are separated by the installation of the of any extra support reactions, and we assuming only rotation this one support reaction for the moment m1, and not rotation of other, and not the motion, the linear motion of this one, just a straight motion, this definite one supporting rod, and not rotating at the second one, sliding, embedding, etc. Just only rotation of this one. And we have the distribution taken from the directory for standard beam, which is the embedded on the left hand. We can rotate this beam to horizontal location. Easy to understand the correlation of the directory standard options of the beams. For example, I can indicate this in the another one part of the presentation, but okay, no, yeah, like this one beam. So we have angular rotation for just only, this is from the directory. Previously got decision for to support it statically indefinable single span beam. So for the rotation equal to 1, we have the moments at the end, and the diagram got already for this definite one. And we have the very many cases of the loading of the single span statically indefinable beams in the directories. We use this to do the diagrams of the bending moment for the main system of the assigned system of displacement method. And we can find here, using this, that the bending moment here have to be the product elasticity modulus by II is the moment of the initial transverse section of the left one stand. And we have another one, just the moment just a half. This because rotation here for the unit, and here could be not the unit rotation, but here we have the unit rotation for the angle equal to 1. And on the other side, because this is a sliding embedding connecting of two rods, the left one rod a stand, the right one just a beam. And we have the same on behalf of action of this unit displacement on the right one part in the two connected in this definite one embedding. But here we have two product by E by I, and here we have E product by I. This in this definite one embedding. Why this more? Because the length, this is 2L of the assigned system. 2L, and here we have the spent 1L. So this is L is 2 meters, this is 4 meters stand. This is the span of 2 meter. The stand is 4 meter. And okay, so this for the first rotation of the first extra embedding for just only one, and the rotation of the second extra embedding for the one gives us with the same standard decision from directory the how much have to be the which is the magnitude of the bending moment on the left part for in the diagram of linear diagram. We don't consider the distributed load here because this is a diagram only under the kinematic action of the unit one rotation of this definite one embedding. Just we consider what if it rotates. So we have the magnitude here on the left, two product by E elasticity modulus and by I, the moment inertia of the transverse section of this horizontal beam. And for the right one, we have like here 1.5 product by E by I moment inertia. This is characteristics of the rigidity of this one rod. So we have the displacement units. So exactly to find the moment, we have to consider the rigidity as is bigger the rigidity of this transverse section of the rod. So much is the moment required to rotate for that just only one. The displacement is not so much important. What one is dimension not important. This is definite one case. But here we came to zero. That's because we consider another one standard scheme as for single span two supported beam. As on the other hand, we have the sliding hinge of the beam. So here we have a triangular shape of the diagram of the bending moment and action, kinematic action of the unit displacement, and the straight displacement, the translational linear displacement and action of the force, and action, kinematic action of the unit displacement linear, not rotation, but linear displacement. Yeah, we assume that for the displacement method, we do not consider the change of the length and action of the longitudinal force. So, and action of this displacement, these two nodes will move for the same magnitude. Yeah, as we have here two hinges. So this is last one scheme of the standard two supported statically indefinable one span rod, like this one previously taken. So we have the linear diagrams of the bending moment, and here as we have two sides embedded, just only one by sliding embedding, the embedded the stand. We have the bending moment at each of the ends of the other sides, and we, and the action of the displacement, we determine the bending moment diagram on the stretched fibers of the element of mechanical system. So this is stretched fibers, the stretched fibers on the left, this on the right, this is below the rod, is above the rod, the stretched fibers. Exactly for the other diagrams as well. Yes, and as well we can use for the mechanical system, the main mechanical system that is divided into the supported parts of mechanical system by the introduction of the extra supporting rods in accordance with the number of the static, kinematic indefinability of this mechanical system. The system is 3 times kinematic indefinable, and 4 times statical indefinable. So kinematic is a little bit less indefinability. So this is a left stand of mechanical system, and this stand is embedded by 2 ends, and if we will find in the tables of the directories the usual bending moment diagram or the corresponding single span statically indefinable 2 ends embedded beam of the even distribution of rigidity along the span of the beam, we can find that here will be the diagram as indicated on the left stand in the 3.16.2D. Yeah, this is the angle of the connection of 2 branches of the diagram, just because this is a point of the application of the concentrated force. Besides, for 2 elements mechanical system, in between of 2 extra supports and action of the external load, we have here the parabolic shape of the bending moment diagram determined on the stretched fibers of mechanical system. So you have application of the distributed load downwards. So the stretched fibers is below here. So we have this one shape of the diagram. This is a piece of the mechanical system embedded by 2 ends, single span, statically indefinable rod within the embeddings. And here, statically indefinable rod, yes, but here on the right end we have a hinge. So as for the equality to 0, the bending moment on the hinge, we have another one shape of the bending moments, a bigger moment bending in the bending moment in the embedding here. This is 3 diagrams of the bending moments which cause the first, second, and third diagrams shown the bending moments in the elements of the mechanical system under the assumption of the unit displacement in each, consequently each one of the introduced extra connections due to the number of the kinematic indefinability mechanical system. And the last one is the main mechanical system diagrams and the action of the external load. All these diagrams got by the use of the standard decisions available in the directories online or in the textbooks of the structural mechanics and the chapter of the use of displacement method for the decision of statically indefinable mechanical systems. So this is kind of the advantage of the displacement method, as we can consider, figuratively speaking, consider the displacement method as a distribution of the issue to decide static indefinability from the integral mechanical system into the previously decided statically indefinable single span to supports with the 2 supports standard and the usual beams available in the diagrams. Okay, now we have to find the factors in the canonical equations of the displacement method. This is a canonical equation of displacement method. So the first one equation, yeah, I will next come a little bit back, but I have to indicate what the factors we have to find, because in the next we will use these factors in the canonical equations, in the system of canonical equations. The first equation is total of forces acting in the first one assigned extra supporting connection. This is on the left up corner of the assigned mechanical system. This is a sliding embedding. So this embedding experiences in the assumptions experiences the rotation, unit displacement, angular, and what is the efforts, not forces, but if you consider the angular displacement, this is a moment in the taken from the God diagrams of the bending moments of the elements of mechanical system in the main system. main mechanical system and action of the unit, kinematic action of unit displacements. So the factors first in the equation on the left is the forces which rise due to the unit displacement, consequent displacement of the first displacement next to the second one is not the simultaneous impact of the displacement. Consequent displacement in each of the added extra connections in the usually in the rigid nodes of the mechanical system assigned or in the hinges just to constrain the translational displacement of hinge in the main system, like the methodic assumptions to determine the canonical equation. So this is a force, not force, but could be effort, could be moment, because this angular displacement, this is rotational displacement. So this is a moment which we have to have, which will be on the first in the location of the installation of the first extra connection. If this connection will rotate for the, if we would like to rotate this connection for the angle of unit angle, rotation angle is Z1. This is a force which corresponds if we rotate this for the Z1, which moment, not force, but the moment will appear in the definite one support, extra support. So this, what is the force, what, excuse me, that 2 is exactly the angular displacement of the second embedding. So R12 is what is the moment rising in the first extra connection if we rotate for unit 1 angle the extra support Z2, etc. So, and this is for the next equation the same. In this definite one issue, we consider 3 equations as we have the system of 3 times the kinematically indefinable. So, and on the right end of the equations, we have the free summons. Free summons is what is the force rising in the this first equation. And the force extra connection, not force, maybe effort, but effort. At the definite one case, this is in the embedding, sliding embedding one. This is not force, but moment. If we have the load assigned for the mechanical system. And this all efforts have to be equal together to 0 due to, we assume that actually we do not have the extra connection. This is methodic approach to have the canonical equation. This is for all of extra connections. In our case, we have 3. Okay, let's come back and find what is the unit force, excuse me, unit moment, unit effort arising at the action of the unit angular displacement. This moment, actually we say unit, but this is not the unit moment. This is the moment arising under kinematic influence of the unit effort. Unit effort is the unit kinematic action, not the effort, but the R11 is effort in the force direction of the constraint in the first extra support and of the rotation, these constraints, and the action of the moments which under action of the unit sorry, but under action of the unit kinematic action of the unit angular displacement of this definite one support is the assumption of the displacement method. So let's consider this force diagram on the this embedding connected to rods as vertical stand and this horizontal beam, and here on the left we have the rotating moment and we have stretched fibers. The left one is this definite one piece of the stand. The magnitude maximal is the product E by modulus elasticity by the moment inertia of the transverse section of this beam I. And this rotates counterclockwise. And we have here another moment on the another side of the embedding is equal to 2 product by E by I, rotated clockwise due to the stretched fibers, the low fibers in this. And other here we have the, because we just cut out the node that we consider the balance of the node, and we have to have the balancing moment. Balancing moment is R11. So R11 equal to, if we consider these two taken together, so we will have that is R11 equal to 3 by E by I. We have to have the rotating moment equal under the kinematic action of the unit rotation angle equal to 3 by 3 by E by I. And after, let's consider the diagram of the to find the what is the rotation moment and action of the unit kinematic action of unit displacement in the second embedding. So we have second embedding, we have the diagram of the action of second embedding. We have on the left hand of the location of the first embedding, the rotation moment is equal E by I, E modulus of the elasticity. This diagram we got using the standard diagrams for single span two supported beams. And due to the balance equation of definite one node, for this second diagram, we have that the unit effort in the, because this embedding this unit moment, not unit moment, it the moment and the action of the unit displacement in the moment in the first support and action of the unit displacement in the second support. So the diagram has to be on the second case of the assuming displacement of the and the embedding angular displacement of the sliding embedding. But we have to consider the left one magnitudes. So we have that R12, the effort arising. Actually, the effort is the moment is not so, equal to E product by I. It's not so much important to consider what is the R with the indexes of the direction of the effort application, and the second is the direction and the point of the cause of the effort arising. So it's not so much important to consider what is a physical sense, because it's rather formal. Actually, it could be just or the bending moment and the kinematic action of unit displacement, or it could be the forces and the action of the unit displacement of the unit one supports, extra supports. So on behalf of the lateral displacement, so we'll consider the diagram of the bending moment in the first extra connection. If we assume that the right one extra connection installed to the main system when doing this out from the assigned system, if we assume this translational displacement Z3 equal to 0, equal to 1, excuse me. In this case, we have definite one shape of the diagram of the bending moment for this definite one point, 0.375 product by E by Y. So if we move this end for just magnitude 1, what one? Not so much important. This is just a unit, theoretical concept. And this is the magnitude, and due to the balance equations, we have that R13, the rotation moment in accordance with the conditions of the balance, using the static method of determination. This is static method of determinations of the factors and the free summands of the balance equations of the displacement method. So we find that this is minus 0.375 product by E by I. And the last one, we have to find the the free summand of this balance equation. Like here we have free summands, and we have to find this free summand. We use the lower diagram. This is a lower diagram, the diagram of the bending moment of the main system of the displacement method. So when we share, when we divide the assigned mechanical system into the set of the single span two supported beams and statically indefinable, and we can use the previously had the decisions for the other kinds of the supports and load distribution for the single span to supported beam, and in the standard decisions from the directories and from the textbooks. Exactly, we can decide do decision the statically defined two supporting beams ourselves. It's not so much difficult by the forces method, maybe, I don't know, any kind of the question of the compatibility of deformation for each of the kind of the support of the single span to supported beam. But this excessive efforts we have not to do that. We can use just only the previously have had decisions from the directories or from the textbooks of the mechanics. So under the action of the external load in the left one, we have 2.5. In the left one, rod connected to this first one, and to this first one, extra connection sliding embedding. And on the right, we have one. So under action of the external load, we have here distributed load, and we have the diagram here for two embeddings shape like this one. It's as we remember for the parabolic shape, this is 1/24th part of product of distributed load Q by the span 2 meter here, or just as so this is from the directories for the single span statically indefinable to supported beams. And on the other side, so we have the bending moments and action of the external forces on two sides of the embedding. On the left 2.5, on the right 1.0, but they are of other direction. So actually we have the difference, and the free summand is in the accordance with the balance of this cutout node and action of the external load, considering the main system and the action of the external load. We have that free summand of the canonical equation is equal to 1.5. So we have here 1.5 divided by E. This final transformation of the canonical equations of displacement method could be by the deduct of the common factor or common denominator E product by I, for example, here for this calculus. Kind of the calculation is we have even distribution, the rigidity of transverse sections is not so much important, but just mathematic transforms, how to simplify the form of the canonical equation. Yeah, but before this mathematic transform, we have 1.5. We do not divide by E and I, etc. But here we have the product by E. But next we will cancel the common factor of this here, and here we have the denominator of the cancelled factor here in the canonical equation in the final state. The same for the second slide in embedding. We introduce a second extra connection during the main system of the displacement method of the assigned system. So we can cut out it, and we consider for the first one on the first one diagram we have only one bending moment on rotating counterclockwise. So we have the considering the balance in this definite one support we can find, and which is R log is 2 in second direction, second because point denoted second, and the action of the first effort here we have two components rotating other sides two components rotating in the same sides, because but on other sides of the other magnitudes of other signs, but applied on other sides of the this one definite one sliding embedding. So this we account together with the same sign, and due to balance of this one node and due to balance of this node, second mean under action of the translational assumed displacement of the third extra connection. So it can be due to this one node we have 0, as we can see on the diagram, the magnitude is 0. And as well, we can find this as a difference of these two magnitudes, because they are together here, just on the upper fibers of the mechanical rods, but from the other sides of the mechanical system. So and they introduced in the balance equation with from the other sides, and we have finally the that is the minus 0.5. This is free summand in the second balance equation. It's important sometimes to not make mistakes in the correctness of finding the signs of the bending moments in the diagrams of the bending moments. Is this is appropriately relative, just because in each of the assignments we have to obey just only one rule adopted in the decision of this assignment, if what is the positive direction of the rotation on the flight state of the mechanical system statically defined, if we determine. But usually we consider the bending moment positive if the diagram is above the if the diagram is below the below the considered beam, exactly if the beam is horizontal. Otherwise, we have to theoretically rotate to horizontal location, for example, this one, and we can find that the positive, which is below this beam in the horizontal location, just because it if the diagram is below, it bends the ends of the considered sample upward, because the stretches the stretched is low fibers of the, and this is just usual rule of science of the bending moment diagrams. And when we have the correctly found bending moment diagram with understandable signs for us, we can find the signs of the transverse forces diagram, as we remember that transverse diagram force is in derivative relation to the bending moment. The bending moment diagram is an integral function of the transverse diagram function, and the transverse is derivative from the bending moment. So the signs of these two diagrams are interdependent, but we usually consider for the just only single span two supported beams, we consider the moments as positive, as the diagram of the magnitudes in the diagram of moment positive, if this diagram corresponds the bending the ends of this single span upward. This will be the positive. It could be another one, but we would not make a mistake, and we have to obey the rules. Adopted indefinite one decision. Okay, a little bit difficult could be the finding of the factors for the third one, canonical equation of the displacement method, and consider it as sure. That's why if we have the translational displacement on the first one, we have to find not the bending moment, but the force. We adopt the assumption that due to the within the displacement method, due to the we not consider the longitudinal forces action on the change of the length of the elements of mechanical system. So we assume that horizontal displacement of the hinge and the if we just assume the unit displacement of the hinge or 3 and the extra as the part of the extra support installed to the hinge 3, the horizontal displacement is the same as caused by the displacement, the horizontal displacement of the sliding embedding 2 and the sliding embedding 1. And that's why in third direction, we consider the first factor as equal to 0.375. How we found it? We consider the derivative dependencies between the bending moments and shearing forces. As a shear force action on the left one stand, for example, we consider it as sure. In the sliding embeddings on the first node, this force transformed into the longitudinal force acting on the third extra connection. So this force applied to the end one acts to the this one extra connection. Due to this force, if only we consider the action of this force and only one factor impacting the force arising in the extra connection 3. But we have no the applied force in the fourth sliding node. We have the displacement available for sliding node, and to find what is the force, we use a derivative interdependence. So considering the diagram of the bending moment here, we have to find from this diagram bending moment what is the longitudinal force here. The longitudinal force equal to derivative of the bending moment. If we have the linear diagram bending moment, and we know the magnitudes at the ends, and we have the span equal to 2L, 2L assigned size, and L, as I remember, equal to 2 meters, 2 meters here. The total height of the stand is 4 meters. So the tangent of the inclination of the angle of or the transverse force here is this magnitude E product by I of the first diagram and minus the magnitude at another one end. But from this we have to deduct what this minus, and this is over the other side, minus, so two minuses is the plus. So actually we have the difference between these two magnitudes, 1.5. And if we divide 1.5 by 4 meters, 4 meters is the length of the stand, we will have the derivative, the magnitude of the derivative equal along the all length of the stand. So evenly distributed transverse force is E product by I minus, in the brackets, next minus 0.5 of the another magnitude of the sine divided by the length of the stand 4. And this is 0.375 by E by I. And this is the R31. So this is a force on behalf of the force acting in the direction of the third extra connection installed when doing the main system out of the sine system, and this force which arises if we rotate the first sliding embedding, assume the rotation per one. So in this definite one action, the rotation per one, what one is not so much important, just the one, the theoretical concept of the rotation angle. This causes the displacement. This causes the force arising here in the third connection by 0.375 product by E by I. like a derivative of the this left one diagram of the bending moments. The diagram of bending moments when we rotate the forced extra support do not cause the forces arising in this translational direction due to the forces, transverse forces for the bending of the horizontal beam do not have the projection of the line of the action of the force which arises in the solid embedding. So this is a longitudinal force applied leftward here, like indicated here. But this bending is in the another plane, and this bending of this element mechanical system do not cause the longitudinal force. It causes only transverse, not acting this one force arising in the embedding. So we have only impact on the embedding force arising of the force in the embedding by the angular displacement in the first extra support due to the bending of the vertical stand. And we find like the transverse force by finding of the numerical finding of the derivative of this diagram. The derivative is even distribution of the transverse force. So if we rotate second the bending, how does it impact on the force arising in the third extra connection? Do not have influence, so we have 0. Why 0? Because the rotation of the second embedding caused the embedding moments in the horizontal beam, and the transverse forces are in the horizontal beam. And if you consider the balance is a definite one, angled hinged connection of the vertical forces transverse and the longitudinal. We don't have the longitudinal forces applied to this definite one hinge when we do the unit angular displacement of the second second extra connection for the mechanical main system of when doing this of the assigned system. And we do not have the impact of any bending of the vertical stand here in the middle on the when we bend the system. We do not bend this vertical stand as we have the hinged connection to the vertical stand. So here we have 0 impact on the forces arising in the third extra connection under the rotation of second sliding embedding as well introduced when doing the main system of the assigned system. And for the third, we have the third, if we assume the unit displacement of this total assumed horizontal displacement of the these three nodes straight total displacement in the direction R33 of the installation of the extra connection, his extra simple rod supporting. We can consider this all diagrams of bending moments and the angle of the inclination the subject to find the forces arising to this one. Transverse force we have to find due to these 3 bending moment diagrams as a numerical derivative finding of these diagrams, 1 and minus second 1 divided by the length of the stand, this one minus this one divided by the length of this one. But in each definite one case, we will find what is the transverse force. Is any kind of the even distribution of transverse force in all stands if we moved the left one hinge here on the right translationally moved and assuming that the length of the beam do not subject of change under the longitudinal force. So this all nodes will move for this definite one magnitude of the displacement. And these three forces will act on the force together in the balance arising in this definite one node. Consequently, after kinematic application of unit displacement of this node rightward, as we assume. So, and we have this total of this all magnitudes of the transverse forces in all stands at the upper ends of each of the stand. Impacts the invisible balance of the force have to be raised in the extra simple supporting link here with the hinge. And what is the free summons in third equation? As well, we consider that balance of the forces on the vertical stand here, because other stands do not have the transverse forces, and the transverse force in the horizontal stands do not impact into the force arising in the this one horizontal one extra connection. So the distributed load practically do not impact on the force arising free summand and the balance equation of the total of all forces acting and the right extra connection on the left one, and how to find this force action is equal to the transverse force in the vertical stand. Considering the diagram of the is a Brooklyn line consists of two symmetric segments relative to the point of the application of the external concentrated force. The transverse force here applied to the end equal to 2.5 minus 2.5, these two magnitudes, minus. So this is of the other sides. From 2.5, we deduct minus 22.5. This will just like a plus. So the difference of the two magnitudes is 5, and divided by 2. 2 is a span between the point of location of this concentrated force and the upper and the upper of the rod of the stand. This is to this one connection. So, and we have 2.5. So 2.5 plus 2 minus 2.5. This is 5 divided by the arm of 2. And we can find that we have 2.5. This is free summand 3 and the action of the external force of the canonical equation of displacement method. And the details we can consider here, like how we can find the forces 1, 2, etc. on behalf of the deformation of any of stand to and the action of the considered indefinite one case the displacement action, kinematic action of the finite displacement of each of the unit assumed rotation or translational displacement of the extra installed a connection for the displacement method. Finally, we after the substitute have the equations. We can decide these equations. We can use a mathematical determinant method in the algebra, or we can just only gradually from the first one derive which is z1 by the z2 and z3. And next we will substitute in the second, and we'll have two variables in the second after the substitute, and we will derive, for example, what is z2 derived of the z3. After that, we can substitute consequently this all into the last one equation and find, for example, z3. After that, return to the previous one, find z2, and return to the first one after them transforms and find that one. This is just the approach how to decide the algebraic equations, canonical equations, and we will have all displacements. After finding all displacement, we can substitute these displacements in the canonical equations using the got before factors in the sum of canonical equations, and we can find the forces arising in the nodes which in we making the main system of the assigned system, which in we installed the extra connections. This is the displacement method. The benefits of displacement method, let me please repeat, is that we can use the previously had decisions of the statically indefinable single span two supported beams from the directories. So practically this could be a less of calculations using the displacement method. Exactly, it requires definite experience to use. This is a sample, so it is a single span two supports beams within the main system after the separating the assigned system into the main system of displacement method by the introduction of the extra supports in accordance with the kinematic indefinability of the assigned system. If we have this one, the shape of the diagram of the bending moment, and what is the magnitude of the bending moment and the support reactions, here we have the previously got results. And we have do this in definite each one case ourselves if we have no directory for the single span, by the forces method, etc. Any kind of the equations of the deformation compatibility for the single span elements of the assigned system when doing the system. Another one is two embeddings, and if we have the bending angle, for example, this definite one embeddings rotates for the angle unit angle, what will be the bending moment diagram and the forces and the magnitudes of forces arised due to the definite angular displacement of this embedding. With not the distributed load, not subject to find by what way we have this kind of the displacement. No, just but if we have the displacement, what will be the diagram of the bending moment and the magnitudes of forces and moments. Another one, if we have rotation of two embeddings on the left and on the right, what will be the bending moments and diagram, how it looks like, and what is the magnitude of the diagram. It could be the element of the main system after the determining the main system of the assigned system, considering the degree of it static, sorry, not static, but kinematic indefinability. A little bit difference of static and kinematic indefinability. Because static indefinability corresponds the number of required extra equations due to the to complete the balance equations. We have only limited number of the balance equations for statically definable system, and we need to have extra equations of the compatibility of deformations. For the displacement method, it could be another number of the balance equation. It could be another number of the compatibility of deformations, because kinematic indefinability as a total of the angular indefinability, so how many rigid angles, rigid connections of the rigid connections of the elements has the mechanical system, and how many is a possibility of linear displacement, how many linear displacement is characteristic for the hinged scheme of the assigned mechanical system if we substitute all nodes by the hinges of the mechanical system. So this could be another one sequence of definition of the kinematic indefinability and the static indefinability. The number of the canonical equations used could be other, and that's because displacement method adopted actually to use of the got beforehand previously had decisions for the single span to supported statically indefinable beams. Another one, if we have the on the left the support, and the second support is the embedding rigid, and if we assume the shift of the right one embedding for the unit displacement, how it look like the diagram the bending moments, and what will be the magnitudes here, magnitudes of the bending moment, and the support reactions arising in the assume of the shift of the second embedding per one displacement, one unit displacement. And the next one as well, but on the left we have the embedding, and on the right we have the hinge, just simple hinge, simple supported hinge. So if this hinge will move exactly for unit displacement, what will be the magnitude of the bending moments on the diagram indicated 317.6 B, and the magnitudes of the rising bending moments and the forces and support reactions, questions and come, etc. Just the number of options of single span two supported beams not limited to the considered set. There are very many options of the loads, and this is very helpful for determining the diagrams of the bending moments and transverse forces and support reactions for the single span two supported beams as an elements of the statically indefinable mechanical systems. 3.16.1 determination of the degree of kinematic indefinability of mechanical system, taking into account the linear and angular mobility of nodes. First, we consider we can consider the angular mobility of nodes. This corresponds to the number of the rigid nodes of the mechanical system, and the number of the linear kinematic indefinability we can find as if we consider the hinged scheme of the assigned mechanical system. So in each node, if we will substitute the connection by the hinge, what will be the degree of static changeability of the mechanical system? How many independent geometric transformation of the hinged scheme we can have? And the total will be the degree of kinematic indefinability of assigned mechanical system. 3.16.2, the use of floating embeddings to eliminate angular mobility of nodes, and the use of additional support rods to eliminate linear mobility of nodes when forming the basic statically definable system of displacement method. We consider abstract concepts of the extra connections for the displacements method. The one abstract usually used is the extra support as a sliding or floating embedding, the assumed theoretical the extra connection for the considered mechanical system, which limits the angular displacement of each one node. Usually we install this extra connection, making the main system of the assigned system. We install this extra connection as a sliding embedding in the rigid connection of the elements of mechanical system. If the elements of mechanical system connected in the definite one nodes rigidly, with no opportunity to change the angle between the elements of the mechanical system connected on the definite one node. This we can use the floating embedding, and if we consider the mobility of the hinges, and we have to constrain the mobility of hinges of the connection of the elements mechanical system for the assigned mechanical system, we can use the simple extra connection. And sometimes could be another kinds of the extra connections, but usually we use sliding embeddings, limiting the angular rotation of the elements mechanical system, and we use the linear extra connections, which limits the translational displacements of definite one points of the mechanical system. 3.16.3, determining the diagram of the bending moments of the main system corresponding unit displacement of floating embeddings and the additional support rods and the diagrams of bending moments of the external load. To determine the diagrams of bending moments, we can use for the displacement method when we separated the integral mechanical system into the considered independent elements by the introduce of the extra connections limiting the displacement of the ends as a theoretical concept, introduce extra connections. In the next, we can consider these elements as usually we can consider as a single span with the two supports statically definable mechanical beams, and we can use for that just the got decisions from the directories available online or in the corresponding chapters of the textbooks as, for example, for use of the method of displacements to decide the statically definable mechanical system. We have the previously taken decisions for single span two supported beams, statically definable. 3.16.4, application of formulas of bending moments corresponding to unit displacements and reactions in typical statically definable beams for use in determining of bending moments diagrams of main system. If we have the diagram of the bending moment, sometimes we can use that for finding the diagram of the shearing forces, transverse forces sharing. The diagram of shearing forces we can use to find the factors in the canonical equations of the displacement method. If, for example, we consider the impact of the unit displacement, for example, of in the floating embeddings, in the sliding embeddings assigned as extra connections, and next assuming the unit displacement of these connections, how did they impact on the forces arising in the other extra connections like supporting rods, extra supporting rods. Yeah, 3.16.5, using the conditions of balance of nodes of a mechanical system to find coefficients and free terms of canonical equations in of the displacement method. The coefficients, I mean the factors of the summands of the canonical equations, finding the displacements of the as unknown variables for decision of statically definable mechanical systems. These factors we can find by the method of cut of the nodes of the main system and considering the balance of the moments and forces acting on the nodes. And we can find the forces which arises in each of nodes or just efforts, forces and moments arising in each of nodes, and consequent considering the unit displacements, for example, in all other connections, if you consider the availability of the unit rotation in the floating embeddings or unit translational displacement in the extra connections as the supporting rods. So to find the coefficients, we have to consider the balance of the nodes. 3.16.6, assessing the balance of forces on the side of the cut of posts to determine directions for additional support rod. We balance of forces because if the transverse forces acting on the rod of the mechanical system have the projection directed to the point of the considered force of displacement of the extra supporting rod. So we have to consider the derivative interdependence of the diagrams of the bending moments and the sharing forces of this one of these elements of the mechanical system, and finding the using the diagram of dependent moment, finding the diagram of the transverse forces, we sometimes can consider the balance of the another one piece of the mechanical system, like this one, which goes for the same straight line to the direction of the installation of the extra supporting rod. We can find the force arises in which arises in the extra supporting rod due to the displacement of maybe angular displacement of the extra floating impedance installed in the other rods, maybe in the which installed perpendicular could be, or by the other angle to the definite one rod, which passes through the line of the action of the extra support reaction considered. 3.16.7. The reactions in additional connections of main system corresponding unit displacement serving as coefficient of the canonical equation of displacement method. Reactions in additional connections. Next, we can find the reactions in the additional connections, but for the displacement, we found which we use to determine the efforts in the mechanical system statically indefinable. We can use as the extra condition due to the balance equations in the mechanics of statically definable system. The reactions in the additional connections have to be equal to 0. This like the rule of the finding of the displacements of the extra connections, because we have to find the displacement which corresponds 0 magnitude of the forces arising in the extra connections. Due to actually we have no extra connections, is a theoretical concept to determine the displacements. So finally, the displacements correspond God of the extra connections in the points of the installation of the assumed of the connections. These displacements corresponds to the external load and correspond the equality to 0 of the forces in the extra connections. But after finding the displacement, next we can find the forces and the elements of the mechanical system. And this helps to determine diagrams of the bending moment, sharing forces, maybe longitudinal forces in the assigned system, if we have the displacement of the main system. 3.16.8, free terms of the canonical equations of displacement method, which are reactions in each additional connection of the main system from the action of the specified load. Yeah, this the approach to find the free terms is the same as to the approach to find the factors of the summands of the canonical equations, which are proportional between the forces arising in each of the extra connections due to the unit displacement of other extra connections. But the product as a summand of the canonical equation of the factor of the forces arising under action of the unit displacement on the displacement as a subject to find as an unknown variable of the canonical equation, the product indicates not the force on the unit displacement, but the force when we will find this displacement of the extra connection. This corresponds to the definite magnitude of the force, not the unit magnitude, but because finally this corresponds not unit displacement, but the actual displacements of the extra connections due to equality to 0 of the force acting on behalf of the external load and on behalf of the extra connections, considering that we have no extra connections, actually, just a concept. 3.16.9, the form of the system of equations of the displacement method when substituting the found coefficients and free terms. The form is a linear form, algebraic. We can decide this or using the, it depends how many equations we have and how many unknown variables. If we have like 2 or 3, for example, equations and 3 unknown variables, we can decide just by the deriving of from the first equation of one unknown variable by the other two, and derive and substituting the second two equations, derive from the second equation the second transformed equation by the derive the second unknown variable, and after that substitute this all to the third equation and find the third variable in the of the magnitude, and then substitute to the previous one two transforms, and we can find 3 maybe unknown variables. Sometimes we can use algebraic approaches as the use concepts of the algebraic determinants, and we can use determinants, and next consequently we can define what is the unknown variables in the algebra. It's important when we have many unknown variables, the use of the algebraic approaches of the matrices and the determinants of matrices or factors of the system of the linear algebraic equations, because we have in the mathematics softwares like MATCAD or Microsoft Excel, we have just approaches to decide of many or systems of many algebraic equations for many variables, more than 3, etc. We have so many as we have just indicate in the tables in the Microsoft Excel or define as the matrices in the MATCAD. So this what method of determination of the variables is up to the definite show. If it's small, we can decide ourselves. If they're big, we can use the software using the algebraic approaches, determination of the unknown variables of the systems of algebraic equations, linear. 3.17.1, this is because a little bit this speech corresponds, this presentation corresponds with the article 3.17 from the book of the indicated originally. Yeah, and the finding of the reactions of statically indefinable beams under standard external influences with unit displacement using the finding in finding the coefficient of the canonical equation displacement method. This how we can use the advantages and preference of the displacement method, because this is distribution of the concept of finding of decisions of static indefinability, the elements of the forces of statically indefinable system assigned to the beforehand got decisions for statically indefinable single span to support beams. And how we can consider what is the usual decisions for the single span to support beams. 3.17.2 examples of statically indefinable beams with a variety of forms of applied external load, as well as options for supporting of pinching the ends. Yes, the set of the good decisions in directories and in textbooks and definite chapters for the use of displacement method for deciding the statically indefinable mechanical system consist of the tables of the options, and there are single span two end supported beams by of the beams embedded by two ends, of the beams embedded by left end and the hinged right end, and beams embedded by right end, hinged by left end, and etc. If the embeddings could move, like to shift mutual shifts of the embeddings, and which is the diagrams of the embedding moments, and we can use next to find the diagram the shearing forces as a derivative, or what is the support reactions, etc., for any particular cases. Thank you.